Hello everyone, welcome back. In this video we are going to describe we're going to discover how to describe a substance with all of the different phases that it can exist. And so phases are solids, liquids, gases. Turns out that there are several other phases beyond those three. And so we often need something a little bit more robust than just an energy level diagram to be able to really describe what state the matter will be in at different temperatures and pressures. So let's get started. Again, like with the previous video, you can find this information. This is in chapter 11 of your textbook. So phase changes, as we were talking about in the last video, definitely involve temperature. So we know that if it's 70 degrees outside, it can't snow, unless you're in Denver. But really, it's still not going, that snow's going to melt by the time it hits the ground because it's too warm. But it turns out that phase changes not only are related to temperature, but they are also related to pressure. And so this pressure component is why you can cook chicken in an Instapot in 20 minutes, whereas on the stove, it's going to take you 2 hours. And so by changing this pressure, we can affect the phases that things will be in and the temperatures that phase can occupy. And so both of these phase diagrams are phase diagrams for water. And some things to point out with phase diagrams is that most things have what's known as a triple point. This triple point is the location where the pressure and the temperature at which the substance exists in all three phases. There's also a critical point in most things, and above the critical point in either direction, either pressure or temperature, are what's called a supercritical fluid. Supercritical fluids have much different properties than gases, liquids, or solids. The most common everyday use of supercritical carbon dioxide is decaffeinating things. It turns out that you can run coffee beans or coffee grounds through supercritical carbon dioxide, and you can remove the caffeine from those coffee beans or coffee grounds without using any solvents or adding any chemicals. And what's really nice about that is that once you change the temperature and pressure and you go back to, say, gaseous water, that CO2 is going to just evaporate. And so you don't leave behind any residue, and you can get rid of the caffeine. So triple point above critical points is supercritical. When on the lines of the boundaries between phases, on these lines, this is where two phases exist at the same time. So at this boundary, we have both solid ice and liquid water can exist. And so that's the melting point. And likewise, this line is where the water and the water vapor. So that's the boiling point. And notice that the boiling point changes and the melting point changes with pressure. Okay, so I kind of talked through this. A triple point, all phases exist simultaneously. A critical point is where a supercritical fluid is created. So, using phase diagrams. At atmospheric pressure, 1 atmosphere, what happens to water when we go from negative 15 degrees Celsius to 25 degrees Celsius? Now, at regular pressure, the melting point of water is 0 degrees Celsius. Or you could call that the freezing point. So intuitively we know that the water should go from ice to liquid water. To find this on the phase diagram, to use the phase diagram to figure this out, what we do is we find our starting position. And so we have 1 atmosphere of pressure, and we have minus 15 degrees Celsius, which is going to be somewhere below 0. And so we're starting somewhere at around this point in a solid. And then keeping our pressure constant, we are going to increase the temperature to beyond the melting point, or 25 degrees Celsius. And so we can see that where we started, we were in solid. And where we finished, we were in liquid. And somewhere in between there, well, around 0, we went through the phase transition, or we melted the solid and turned it into a liquid. And that line indicates that transition. Okay, so let's do another example. So I have carbon dioxide, and I'm asking what transition occurs when CO2 at 2 atmospheres and 197.5 Kelvin is reduced to a pressure of half an atmosphere and at 197. So I'm going to keep the temperature constant. And nicely, I picked a temperature that is on this graph. And so I'm starting at 2 atmospheres, which is somewhere up here. So I'm starting as a solid. And I'm going to keep the same temperature, and I'm going to lower my pressure down to half an atmosphere, and probably somewhere right in here. And that is a gas. And so that transition is called deposition. Messed that up. I had that backwards. We went from a solid to a gas. Going from solid to gas is known as sublimation. Whoops. Okay, so that's how to read phase diagrams. There's not a lot of math to be done here. It's more thinking through what transitions occurring at what pressure and what temperature. The next couple of videos are going to talk about how we begin to quantify the phase transition processes at different pressures and different temperatures. And this is what's called the Clausius-Clapeyron relationship. So stick with me, and I will see you then.